Hi everyone. So here we're going to bring everything together and talk about building the multiple regression model. So let's remember that we build a regression model beginning with two things. One is the actual concrete data set. So we have to have data that we want to build the model on. We also call the train the model. And also we need to have a kind of abstract model of the variables that we think are predicting our outcome of interest. So this here is the algebraic configuration or syntax of how we're going to build the model. And it's going into multiple lines just so it's easier to read. But essentially, you can put it all into one line. So it's interest rate equals the first beta is also called alpha is the intercept, and then plus the first beta coefficient times one variable times another variable, and then we have all the multiple variables. So why am I listing all of these? So all of these are listed because they are potential predictors of interest rate. There's a theory to suggest that bankruptcy can impact the interest rate. The term of the loan can impact interest rate. The debt to income ratio can impact interest rate. The credit utilization level can impact interest rate. So we're not just putting all the data that we just happen to have. We're putting things that kind of make sense in 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 the abstract model that we're building. And there are probably other things that impact interest rate, but we don't have the data for. So we don't use it, and your model is not going to be complete, but that's fine because it's a partial model, it can still be a good model. So usually when we build a multiple regression model, you have to have this understanding of what the variables that are going to go into the model, the potential causal relationships or associations, and the data itself. And then as we have seen, so we then load the data into the algorithm in the structure that we built here in the abstract way. And then the OLS algorithm runs and builds the model, and then we get the results. So these are the results here. And each of these here are the coefficients under estimate. And each coefficient is going to be this beta here. And it's how much the unit increase in the predictor variables impacts the outcome variable. We'll keep repeating this, and you should repeat it to understand it. And some of the other information here, so the standard error is the amount of variation we can expect in the estimate itself. So even though this says 0.997, it's probably 95% confidence that it's between 0.997 plus 0.099 or 0.997 minus 0.099. So it's kind of the range of error that we can expect from the values here. So it's really, we have an estimate is 2.5, but it's really 2.5 minus 0.11 and 2.5 plus 11. This here, the statistics, we don't really need to worry about it. This has to do with where in the normal distribution the values are. And then the p-valence, and this is the important too. So every variable, every attribute that's calculated has its own p-value, therefore its own statistical significance in its association with the dependent variable. So you can see many of these all of these look significant, except this one here. When the loan was issued, doesn't seem to have an association, or not a statistically significant association, but everything else does. So you have to know which of these are categorical and which of these are not numeric. So I remember credit utilization, I think, is numeric. So every additional unit of credit utilization increases interest rate by 4.897. Now, bankruptcy is actually binary in this data set, binary. And so, we can see it here, the data's here. So if a person is bankrupt, it increased the interest rate by 0.391 points compared to those that do not. We always have to remember compared to those that do not have bankruptcy, and so on. So this is how we build and interpret the regression model. So let me give you some general ideas about interpretation of the regression model. So each coefficient, also you can call it a slope or estimate, is the impact of a unit increase of the variable on the dependent variable. Notice the dependent variable is not listed, but you know because you built the model, so you know how you built it, and that's the outcome variable. Now, each coefficient has its own standard error and p-value, as we just mentioned. So you need to look at that too, especially the p-value. So the most important is the coefficient itself, and then the p-value. Notice that we have one that is negative here. It's not significant, but it's negative. So meaning that every unit increase in this thing here, or it's going to decrease the interest rate. It's the only the negative one. All the other ones have a positive relationship. And each coefficient in the model is controlled for all the other variables. So let's just take this first part here. Each coefficient in the model is controlled for all the other variables. So that's why we say on average and everything else equals. On average because, once again, this is a generalization. It's a model. It's not the actual, it's not the data. It's a generalization of the data. And we say everything else equals because what happens here is, so for example, let's focus on bankruptcy. Every person that has a bankruptcy, or let's say, if a person has a bankruptcy, on average, their interest rate goes up by 0.391 percentage points compared to those that do not have a bankruptcy, and assuming all of these other variables equal. Assuming all of these variables equal. So it's controlling for all the other variables. And this is great because we kind of want this control in our analysis because we want to know the impact of bankruptcy itself on interest rate, not the other ones. And we want to know the impact of debt to income on interest rates separately. So we want to know the impact of this, assuming the other variables kind of stay the same. So this is the actual, when we see the estimate here, this is the actual impact or potential impact, or the association really, of debt to income on interest rate, and not really including the other variables, or better said, controlling for all the other variables. So assuming all the other variables stay the same way, the impact of debt to income on interest rate is 0.022 plus 0.022 percentage points on average. And also, if variables are added or removed, it will likely change the value of the coefficient and the goodness of the model, also called the goodness of fit. So the goodness of fit is the good of the model. So if you have a number of variables here, and if you change these, if you just put 5 of these variables, then all these estimates may change as well. And lastly, to talk about this goodness of fit in terms of interpreting the results, let's talk about the R-squared measure. So the R-squared measure is one of the most important measures of how good is your model. And the measure refers to the percentage of the variation of the dependent variable explained by the model. So it's actually kind of easy to understand since it's in percentage terms. So actually, I built a model here from one of the example data sets that I have. And you can see, so you can, here for your records as well, you can see I'm building the LM linear model, and the rate of interest is what I'm trying to predict, the outcome. And then all of these here, income and loan amount and credit score and property value, are the predictors. So I'm hypothesizing that income and loan amount and credit score and property value can explain the rate of interest. These are potential predictors of the rate of interest. So I build the model from the data that I had, and then I get the results of the model here. So it's just like we saw before. So we have the intercept. Intercept is here is 4.24. Now, and here is the estimates or the beta. So income, all of these also are numeric. So each additional unit of income increase this interest rate by 0.00000345. So it's very, very, very tiny, but it is statistically significant. So it's a very, very small amount here in this real data set that I have, quote unquote, relatively real. And so these are the estimates. So here I want to get our attention to this multiple R squared. So you're going to see the multiple R squared and the adjusted R squared, and usually they're very similar. So you can use either one, but note that this is an important measure of how good this model is. That is, how good do all of these variables combined explain the variation in the interest rate? And actually this here's kind of small because it's only 2%. So 0.02, 0.02 is 2%. And 2% explanation and variation is generally considered very small. So this is not a good model. And in other words, we want to add other better variables here to better explain how the interest rate either goes up or down. Okay, and we'll talk about that also next time. So remember how to understand this multiple R squared. And let me just finish here with some issues that we're going to see also next time, so that we need to be aware of. So about model selection strategies. So as I was saying, you need to understand what the variables are that you're going to add into your model and what is going to predict. You don't just add variables randomly. We need to have a theory, we need to have an understanding, and we need to have the data. Checking model conditions, so things about outliers or if there's linear relationships. This is a linear model, so we do want to graph the relationship between certain variables and see if it seems linear before we use the linear model, because multiple regression is a linear model. Also, we need to be aware of variable transformations, and we talked about the dummy variable. This is a variable transformation, so these are things we have to do before we build the model. And there are other kinds of variable transformations we can do as well. There's also, we need to interpret model quality. So how good is the model as a whole? This is an important consideration. So if we build a model like we did before and it's only the R squared is 0.02, so 2% explanation of the outcome variable, that's not good. That's very little. We want something at least like 10 or 20, I would say, and hopefully maybe more, 30 or 40. Doesn't have to be 100%, but it gets complex once the numbers go up as well. And one really important issue here that we also get to talk more about in more advanced statistics and analytics classes is the collinearity of predictor variables. So the predictor variables actually should not be correlated, because the model really only works if the predictor variables themselves are not correlated. But of course, we want them to be correlated with the outcome variable. So that's something to keep in mind, and we'll get to go more in depth on next time. So that's it for now. See you next time.